obviously. For me, as I've been saying, I've been coming to Granada for a long time. I seldom get to come here as a tourist, but yeah. Anyway,
Now he comes sometimes as a friend.
so that's
When we come,
my team's too good. I guess we're. Oh, this is good news. Confirming, perhaps. I hope. I guess we're at time, yes? Yeah, okay. So welcome to the penultimate session, if you call the late morning session the final one. And it is action packed today. I'm tempted to say Martin and the science organizing committee have saved the best for last, but that's never a good thing to say, especially when we haven't gone last, like I didn't. So our first, the subject of this morning's first session is magnetic fields and jets. And Marco Vetter is our first speaker. Marco. And Marco's talk is on the role of magnetic fields in the common envelope phase.
You will get a microphone.
There you go.
Well, thanks first of all for organizing such a nice conference. I'm really enjoying Granada quite a lot. And also thanks for having me and giving me the opportunity to talk about my work a little bit. This should actually be moving. I don't know what's going on, but yeah, you get what I said. So yeah, I'm Marco Vetter, and with my collaborators, we've been thinking about the magnetic fields, or the impact of the magnetic fields in the common envelope phase. And maybe this invitation to you, I was planning to show you a lot of nice plots, as your observers tend to do, and give you the opportunity to think with us or on your own, that's your decision, about the implications on all the beautiful observations you made. Oh, yeah. So let's start from the beginning. Hello. It's not working. Should I just continue? So maybe let's start with the common envelope phase itself. So it's this exotic event in a binary's life, and it's thought to be initiated by an unstable mass transfer phase. And then eventually the companion gets engulfed by the primary. Oh, no, still. By the primary's envelope and experience a gravitational drag. Okay, lovely. We go. Experience a dynamical drag. Spirals towards the faulty companion. In the meantime, either the envelope gets ejected and leaves behind a stable core binary system, like at the top. Yeah. Okay, or it merges and ends up in the situation here. You cannot eject the entire envelope. So this system in general is actually a nonlinear length scale, time scale, and multiphysics problem. So that's quite hard to tackle. And you need special tools to do this. So we are using the Arepa code, which is an finite volume code with MHD, so magnetic fields included, with this fancy grid basically. Other people are using other methods. And I just realized that I forgot to mention all the references. Please see, I don't know, reviews by Ursula de Marco and also Ivanova 2013. And yeah, for the common envelope phase itself. So let's dive straight into it. Just this look in a 3D simulation. So we have movie number one. So we have like a red supergiant 10 stellar masses with a going into a common envelope phase with black hole companion. And after the plunge in, so you see this tight orbit here of the co-binary. The morphology of the system is actually quite changed. It doesn't look like a spherical star anymore at all. It's more like a thick torus, and you see this cleared out panel or cleared out bipolar funnels here. And actually what we find should show up in the meantime. So we look at density patch on. And now if we zoom out a little bit and look at the radial velocity here, we see this nice both bipolar outflows. At this point you might ask, why is this guy talking about common envelope phase of a red supergiant with a black hole companion, he must have applied to the wrong conference. With this hypothesis, you're partially true, because we also see this exact behavior in other systems. So, for instance, here again, radial velocity. For a neutron star companion, and same question still holds true, can be surprised now, but also actually for other systems. Here, now the orientation has flipped, okay? So here is the polar axis, and here's the orbital axis, okay? And you also see this outflows here along the polar direction. Okay, and there's more actually. So also a student, Max Heller, PhD student now, who is running a grid. Here you see the different masses, the different mass ratios, and the different systems we are analyzing. Not all of them are relevant for this conference, but the big picture still holds. I mean, we always see this bipolar outflows. I mean, I did this plot in a very, so if you have any questions, just ask me. Some people, some systems are not that evolved, for instance, this one. But in all cases, you see them. So we're actually trying to figure out how to avoid these outflows in the systems. It's quite struggling. Okay, so you may also ask what is going on. Okay, so we try to analyze this in more detail for one particular system, so this red supergiant black hole system, and so we're trying to describe the morphology and embed this to the dynamical evolution of the system. So here you see quite typical diagram we always show for common envelope systems. So the distance over time, the distance over time in bluish, okay, and the fraction of unbound envelope material, kinetically unbound envelope material here in orange, also obviously over time. And the other two lines are here to confuse you. Just different energy criteria, so different types of measuring the unbound mass. Okay, but I mean, for you, most relevant is this orange line. And if you try to now embed this into a larger picture, we see like we start off with a star, the companion at the surface, and after about 500 days, not even 10 orbits, we're looking at something like this. So we have already like these clear funnels with an angular momentum barrier. We have this nice spiral structures, right? And we go a little bit further, we end up with this system. So this looks more or less already like some sort of a thick disk, right? And here the clear funnel again. And then we start the outflows, and in the later phases, this already, well, doesn't change anymore, right? The point I want to make here is we had a lot of angular momentum transport. So the system transforms from this to this, which is basically attributed by the redistribution of angular momentum there. And you can clearly see this in the slope here. So the trend switches, and this is where recombination hits in and starts to strip the entire envelope in the polar direction. That was the wrong button, so in this direction, okay? So the picture we had in mind was basically this. So we have at the outer part, as I was saying, recombination hits in and strips all of the material by local thermalization of the recombination energy, and in the inner part, we try to make a point with an effective viscosity. We transport material inwards, and this is later on ejected into bipolar magnetically driven outflows. The aspect ratio is quite high, as I was saying. This is not surprising. Okay, so we have this morphology. We have some sort of thick porous disk structure. Okay, we have this more the bipolar outflows. So you now can ask, what impact does it have? I mean, do we care at all, apart from the morphology? And if you compare this to the MHD simulations, you see it actually has a small but a relevant impact. So the final orbital separation is here increased by about 24%. And I'll come back later to this number. It's quite surprising that this happens. And the overall envelope ejection is unaffected. It's just what we find. But I'll explain a little bit later in the detail. Okay, and so to impact the orbits of the core binary, right? The magnetic fields needs to be amplified to a sufficient level to even have the chance to make actually an impact. So what we see, and what was also a confirmation of previous results, is basically that we have this amplification, which takes place mostly in the first two orbits. I was trying to make a nice movie out of this. Okay, same system. So we have the first orbit, we have strong shear around the companion, which amplifies the magnetic fields quite a lot, and then we end up in this beautiful mess Okay, we are already in the third orbit and even further. And then you reach locally equipartition, which basically means that the turbulent energy here in this circularized flow matches the magnetic energy, and eventually drive from this enhanced magnetic field structure. You can already see here these bipolar outflows. Okay. So just give you an orientation for the field strength we are looking at here. Maximum field strength we get is 10 to the 4 Gauss approximately. Okay, so that's that. I mean, we've seen this in 4 phases. So it was more or less a confirmation of earlier work. And you may also ask about the launching mechanism. We also try to study this in more detail. So here you see the B field structure color-coded with the absolute magnetic field strength. Okay. And we have this beautiful helical structure here in the outflows, which then has an implication for the Black-Main mechanism, which allows us to not only transport mass out of the system, but also angular momentum. We also see implications for tower jet mechanism, and there was also another work suggesting that we have some sort of magnetically arrested disk, and we launch by another mechanism here. And we also, I must say, we also see local shock heating, which in theory can also contribute to the mass outflows from the system. And I mean, this might sound very technical to you, but we also see like tracer particles. So we're trying to actually get a feeling of how much mass and angular momentum is ejected through the outflows. Here you see them in blue, and when they get ejected, they eventually turn red. Okay, and these numbers are more important for you. So the wind mass loss is on the order below the mass loss which comes from recombination from the system. Okay, the stuff is launched from outside of the binary orbit, so we actually have confirmation that this is its disk wind. Okay, and a bipolar disk wind, I should say. And also, this was quite neat. We found this lovely formula, which is basically contributed by the outflow of the mass outflow here and the reduced mass of the co-binary. If you have questions, ask me later. So we can now say something about what the impact actually is by measuring all these quantities of the outflows. Maybe you can give more precise numbers than I can from my simulations, and we can try to figure out what's going on there in nature with this particular mechanism. But as I was saying, we're currently trying to understand what the robustness of the system is. So if you think about like your earliest primary state, so you have not that fluffed up primary envelope, so you might end up with a merger. Can we still get these same results? And also the Q dependency, so which also goes in the same direction. So if you have not enough energy available to steer off the primary envelope and build this nice morphological structure that we see there. And then basically, I mean, this is just a list of random events I thought of on Friday evening, shortly before I tried to submit this presentation, but you can come up with creative things, I guess. But yeah, my question would ultimately then be, how does this affect the observations we see, right? We see all these nice structures, just sometimes even convoluted events, and it's hard to figure out what's going on and what to make out of this. And yeah, I would be very open to discussions with all of you how this could affect the observations we see. Also, there are some caveats. So what about radiation? This can affect and will affect the morphology and also the outcome. There's some work by, for instance, Michael Oslo also thought about this quite a lot. And also, from our simulations, we cannot tell how the system will evolve on longer timescales. That's where I was trying to mimic here with this little equation here. So it's quite hard to tell. And also, I want to mention this briefly, another movie. So this done by a colleague of mine, Javier Moran-Frey. And he's a merger guy. He's more interested in explosions and whatsoever. And he was trying to merge here, in particular, white dwarf with a neutron star, but it doesn't matter, independent of the system, so to say. But he also finds these weird outflows, in his case, even relativistic speeds, or mildly relativistic speeds. So this also happens in merger simulations, okay? And I think like we really have to think about the implications on the observations there. Well, I'm actually already done. I mean, should I tell another story?
Thank you very much. Especially for finishing early, it's great.
Can I
Question.
add a remark maybe? If you give me telephone numbers, I probably don't know. Okay, if you ask me particular systems, I cannot give you a good answer.
We can maybe translate.
Yeah.
So thank you for these beautiful simulations. I would like to ask, have you tried to actually apply these, your simulations to an actual observed case of orbital ejection? In my talk, I mentioned the Boomerang Nebula there. You have so much beautiful observational details. You have the mass loss rate in the ejector. You have the central bipolar jets, multiple impact, etc. Have you tried to apply your simulations as a test case?
Not in a dedicated work.
Yeah, I find it somewhat frustrating that, I mean, the common envelope simulation people, theorists do all these beautiful simulations. But they're not applying it to actual.
I mean, there is.
Well,
I don't know why.
I feel your frustration, and also I might object to this claim quite strongly. But you're right. I feel like we should talk more as a community. That's definitely true.
Beautiful work. It seems like you're predicting X-ray emitting jets, and because the velocities is for soft X-ray emission,
Yeah.
thermal and non-thermal. So it would be nice to see if you see that for all of your common envelope simulations. I've been following the work of your group, so I always have this in mind. And if you comment on that, and my question is that can you trace or can you believe from your simulation the mass accretion rate history of your simulation?
So yeah, we don't model it in detail. Would be, I mean, yeah, I was just referring to you. You've been trying this, right?
Clarify, okay, so these are, okay, Marco simulation is a massive one, but the groups have done many others, and these are not what we see, okay, so the post-common envelope central stars or planetary nebula we do know and love that Dave studies are a much, much later phase compared to what Marco and others and myself have modeled. These things have to go through the evolution of the start of the pathway, whether it's in jet form or whether it's spherical, plowing into that material, right? So the only thing you can see of these simulations, if you see a transient, right, where you can probably see some acceleration, some material moving at certain speeds, and then you can directly compare. But these are not directly comparable. The PPN are not these objects, right, where you have still a post-AGB in the middle. This is not this object. So this is connecting the work is critical, and we will, but it's not yet what we're doing. We can't do.
Would you like to respond or?
I agree. There was this particular. Yeah. Yeah, exactly. But I mean, to your question, we don't quite model it correctly. I mean, you can get estimates, but they will probably be too high. So.
Okay, I think this is amazing, right? But so my question is a little bit tying into that. It's maybe half a question for you and half a question for Guy. So the velocities that you see here are much higher than we find even in the systems with jets, right? The post-common envelope planetary nebulae with jets, but it's true that it's not really the same material. So I'm wondering if you can really say anything about what the velocity structure would be like in the actual nebula that comes after this.
Yeah.
So I know that he has been working on taking common envelope models and then doing the late stage hydrodynamics. I don't know. Any idea?
But it's fairly hard to model and hard to make any final conclusions to the actual observations there. I mean, as Ursula was saying, I mean, there must go a lot of water under the bridge until we end up with some peonies and stuff like that. Yeah.
We have to move on to the next talk. Let's thank Marco again. And our next speaker is Mohammed Kashi. And Mohammed's title is Jet-Driven Formation of Bipolar Rings in Planetary Nebulae. Numerical simulations inspired by NGC 1514.
Thank you. Good morning, everyone. My name is Mohammed Akashi, and I'm going to talk about the jet-driven formation bipolar rings and planetary nebulae, numerical simulations inspired by NGC 1514. Well, this work was motivated after we have seen the rings of Ressler in the paper 2025. And we start to work on that, me, Noam Sofer, and Eli Bir. So we use Flash as our experiment, numerical methods. We run jets into dense shell, and we follow after the interaction between them, and we have successfully obtained the rings. So here we go. I will talk about the motivation background, then morphology of this PN, NGC 1514, then our numerical setup, initial conditions, the specific scenario we have proposed there, and then summary and conclusion. So first of all, planetary nebulae often show bipolar and ring structures, as we know from many objects. NGC 1514 is a multipolar, messy PN with outer IR rings, so it's dusty rings. As I think I said before, by Ressler paper over there. Okay. So our key question: how are bipolar rings formed? So jets are strong candidates for shaping mechanism in binary and also terrestrial system. Okay, so this is the planetary nebula 1514. So here we see a complex asymmetric inner structure inside. Okay, and here two outer IR rings detected. This is the first one. Like this. This is the upper ring, and this is the bottom one. Okay, so there's evidence of a multiple jet episodes. So it's likely binary interaction, possibly tertiary companion. So here I show the same object, planetary nebula 1514, but first I show here the inner part, which is messy, by David Jones in 2017. It's optical. Here we see lobe, here we see ear, another ear here. Here we see rings. This is the south lobe. This is the same nebula, but this is the outer part, as I showed before. Here we see also inside arc. Okay. Here we see the same, but as we add the main axis, this is for our simulation. So since we need the axis XYZ, so this will be the Z axis. Okay. So here we add the circles that was added by Ressler in his paper. And here in the dashed red one is it was added by us, as we think it should be. So the proposed jet-driven scenario is as the following. The first phase is binary enhances RGB mass loss. Then we have dense shell. So we have assumed already that we have a dense shell on the grid, and then we have an accretion by companion, and jets are launched from the both sides. The third phase is possible terrestrial companion that we think it's responsible for the messy structure inside. So it might be inclined jets, and then we have the messy inner PN. Jets interacting with dense shell form outer bipolar rings. Okay, so in this work we have concentrated only on the interaction between jets and the dense shell in order to obtain the rings, only the rings, without the inner part. Okay, the inner part could be made by other simulation. Okay, I need to add here that several years ago, Noam and I have simulated such nebulae which are messy, as we see in the inner part in this nebula. Our numerical setup is as the following. We have 3D hydrodynamical simulations, flash code. We assume dense spherical shell of mass 0.1 solar mass, velocity 10 kilometers per second. Then we have the jet slumped there of velocity 800 kilometers per second. the m dot mass loss rate of each jet is 10 to the minus 4 solar mass per year, and the jets are active for 48 years. Okay, I must say that I have played many with the parameters, mass loss rate, velocities, and until I got the rings. Okay, it was not easy at all. The half opening angle of the jets is also a very important parameter. I have used 45 to get over there. So two regimes tested also, a non-radiative with the adiabatic index 5/3, and we also simulated cooling dominated with the two kind of simulation. The first one with lower gamma, 1.05, and the second one is with explicit radiative cooling by Sutherland and Topita, the tabulated value, which I added to the code, and I got new energy in each cell in the code after cooling. So here I show our result. This is the meridional plane XZ. So the simulation is three-dimensional, but this one is one slice. Okay, XZ or Y equals 0. The size of the grid is 2 10 to the 17 in each direction. So the total 4 10 to the 17 centimeter, and here 6 10 to the 17 centimeter. So here we have the shape that we got after the interaction between the jet. The jet was blown or launched this, okay, something like this, the first one, and the second one to the bottom side, okay? So the jets carve bipolar lobes and compress the dense shell here, okay? So barrel-like structure we have, it's like a barrel here, and hot central bubble compresses the shell, okay? Relative instability is also naturally developed, so we have a filamentary structure here and here, okay? So what is important here, what I'm looking for are the rings. So this interaction actually produces thick, prominent double rings, which matches actually NGC 1514. Okay, here I'm showing the time evolution of the same simulation, and this at the beginning of the interaction between the jet and the dense shell at time 60 years, and then 140 years. We already can see here this is the cross section, so the ring is over here. Okay, and here is in the same simulation, but at later time, 220 years. Okay, this is a very important slide in which I show what we see actually in observation. So I plot here the integration of rho dl density times differential of length, okay, along the line of sight. Okay, so as I integrated it along the line of sight, I got the following for the first time, and then here in the second time. The most interesting is here. Okay, so here at the up we see this ring, and here the second ring, and you see here also the dense region, as we see also in the real observation. Okay, I simulate the same simulation, but with a lower gamma. We see here thinner rings, which we not really like. The first one is much proper than the first, and also the same times. Okay, 60. Okay, here I simulated the same run, but with a thin shell. In the first simulation, I have chosen the thickness of the dense shell 10 to the 16 centimeter, but here I choose 10 to the 16 centimeter, and we also get nice results. Okay, here I'm showing it in different inclination angles. The inclination angle is the angle between the line of sight and the z-axis of the simulation. Okay, so here we have added in the yellow dotted line or circles here the rings. Okay, here in the red color is the line that was added by Ressler in his paper. Okay, here is a planetary nebula that we have seen many years ago, and I was so confused about that. How can we get such a shape? So now finally I can understand if we are really correct with our model. So it seems to be that there is a jet here that collides with the dense shell. So we get this ring, as we see here, the other ring, as we see here, the dense region like this, the arcs or whatever. Okay, also the inner part, okay, as we see here. Okay, good. Yeah. Okay, so I added here wider implications of our work. So jets can form polar and circumjet rings, implications for binary evolution, stable and unstable mass transfer. Even without the common envelope evolution, jets can dominate shaping. Okay, so it's relevant also to planetary nebulae, core collapse supernovae, and AGN. So here we use our knowledge and experience in formation and shaping of planetary nebulae in the context of supernovae and supernova remnants. So here we go. So this is another work that was done by Noam and I assumed a dense shell into a stellar model of we took it from MESA, and then we launched 2 jets, okay, narrow jets actually, 5 degrees, for example, here 10 degrees, and this number is the kinetic energy of the jet in the units of 10 to the 55 erg. Okay, so you can see here the rings that we got. We try actually to understand what's going on here in this supernova. As you can easily see there, not easily, okay, it's complex. There are many features here, but we concentrated only on the rings here. Look at this one, and this one, the ring. SE ring and the NW ring here, okay? So we have tried to simulate it in this, but please notice the time scales. Second, not as before in the planetary nebula context, it was the years. Okay, so to summarize, so NGC 4050 outer bipolar rings likely shaped by jets. Dense shell and jets give rise to ring morphology. Non-radiative flows essential for prominent rings. This supports major role of jets in binary, also terrestrial evolution. For a future work, maybe we need to include eccentric orbit, inclined jets, also similar mechanism in AGN jets, and as we showed recently, the first time also in core collapse supernova. Thank you.
Thank you. Question in the back from Dave.
Thank you, it's really great. So, I mean, you mentioned it there, I'm wondering, so the central star of NGC 1514 is very eccentric, right? It has an eccentricity of like 0.5. So I'm wondering if you have an idea already of what kind of implications that might have. Would you expect the dense shell with enhanced mass loss from the binary, would you expect it to be spherical as you have in your models, or will it have departures from sphericity and that will impact later?
Yeah, we did not think yet about that, but I think, yeah, it would give rise about the same result. But we need to think about that.
All the way over here. Marco?
Thanks for the talk. I was wondering about when you mentioned the momentum fluxes you assume for your outflows. So you're talking about jets, but jets are in a different community used as highly relativistic outflows, right? Highly concentrated with a lot of momentum.
Yes.
So I was wondering if you have less momentum available in the outflows, does it affect the shaping potential of your sphere?
Yeah, that's a good question. Actually, the linear momentum of the jet gave rise to different shape of planetary nebula. For example, here in my work, if I use a lower linear momentum of the jet, I would get the dense shell with an ear. I tried that. And if you use a higher value of the linear momentum of the jets, you will have the jet break outside and the material, and then you might not get the rings. So to have the rings, it was a difficult a simulation to how to find the specific regime of values of the linear momentum, kinetic energy, mass loss rate, and velocity.
In the back.
So, I mean, first of all, beautiful simulations.
Thank you.
We very well know, of course, from work by Noam and you guys, that jets can carve out bipolar cavities in pre-existing AGV shells very easily. So jets carving out cavities is nothing new, right? What I see here new is that your jet has a very wide opening angle.
Yes.
That is essential to producing these rings.
Yeah.
So my question is, what is the physics behind, and objects like NGC 1514 are very rare. For example, Mike Ressler, after he found these rings in the Weiss data, made a big survey. He didn't find anything else which looked like this object. So what are the special conditions which are producing a jet with such a wide opening angle? I think to me that's very important.
Yeah. So in our simulations, we only assume that we have a wide jet or a collimated outflow. But what exactly caused that, I don't know. I'm sorry. Yes.
We missed the one in the back, I guess, but we can wait until the discussion. Yeah. I'm sorry.
Yeah, my first question was also related to the opening angle of the jet. And the second one is, you said, I mean, you showed that you progressively are forming these rings as time goes by. And is it possible, I mean, to get that time? I think in the last simulation, you got the rings were formed after 200 years. So will we get this kinematic age if we measure like the expansion, the kinematic age of the rings, like considering the expansion or?
Yes. So if we continue the simulation,
Of the time.
Yes. Yeah.
We have time. I think we have time for the question just very quickly. If it's quick.
Question: does flash code have any variable related to the chemistry of the planetary nebula?
Yes.
That you have.
Yes.
Beautiful.
Yes.
So
it has, but
know about for example, the dust molecular composition, like the silicate or.
Certainly.
So if you change, the outcome of the simulation will be changed.
Yeah.
An interesting point. Thank
Thank you
you.
very much.
So we have to move on. Thank
you
you very much. Next speaker is Laurence Sabine. And Laurence's talk is titled, if I can juggle walk and chew gum at the same time, probing magnetic fields in evolved intermediate mass stars, new observational insights.
Okay, thank you. Okay. Okay, so presentation. So
perfect. So good morning. So I'm Laurence Sala. I'm working at UNAM, and today I'm going to talk about magnetic fields, but from an observational point of view. So what we're going to go through today is I'm going to talk about the magnetic field variability in post-AGV stars. Then we're going to jump to dust polarization study, and I'm going to finish with my conclusion. And the most important thing will be the prospects. So let's talk about magnetic field variability, but in post-AGV stars. So why are we doing that? What do we want to know? We want to know if the magnetic field is variable. We want to know if that variability is associated to any physical phenomenon, and why it matters, how it will be useful. So to do that, we're gonna use two objects, RSQT and H-Monocerotis, just because those are the only one with the detected magnetic fields. Those are two Ervitory type stars. Just for the reminder, so Ervitory types are luminous pulsating variable stars, and they have alternating deep and shallow minima when you examine their light curves. So first, RSQT. So RSQT, magnitude varying between 4.2 to 8.6 magnitudes. So we studied that object in 2015, and we already suggest that there was a variability. So George Elvenat in 2023, they did a long spectroscopic survey using Narval at the TBL in France. And here that's a picture, so you can see the light curves. So in red, those are when the observation were done. And on the top, you have the magnetic fields measurement. So the square are the definitive determination. The square are the marginal detection, and the circle are the non-detection. So you can see that you have some sort of change with time. So the monitoring period was from 2014 to 2019, and what it detected is a change in magnetic field that can be estimated between 1.5 to 3 Gauss. So just to remind you that we are talking to very faint magnetic fields, so we have a very faint polarized signature. The variability, the period of the V-Stokes variability was around 2-3 months, but be careful. In those objects are not clocks, so you have changes along the with times. So when we studied the profile of the I and V-Stokes signature, so we can see that there was a connection between the shock waves that propagating outwards from the photospheres and the detection of the surface magnetic fields. And this is really important for what's following. So, and we estimated that that would be related to the compression of the magnetic field lines. That's why you can detect that. So this is the last work that we've been doing. It's studying luminocerotis. So here are the magnitude variation, the period of the object. Again, our first work suggested the variability. So you have here the same plot with the light curves and the observation that we've done with Spirou, Espadon. We use Narval and NeoNarval. So the monitoring period, including our first data, was from 2015 to recently 2025. So one problem with that object that it can only be seen, well, I would say well seen at above 30 degrees elevation, only around 2.5 months in winter time. So this is not the best time to do observations. So sometimes we do not really have good data, let's say. Something also important is that the monitoring, so as I said, was done with Espadon, Narval, NeoNarval, but we also did an infrared interferometric survey using Chara at the same time. So here you have the stock I, Q, U, and V data. So those are data on 2021 from the 13th to 27th of February. So here you can see the variation of the stocks E patterns, and those double reverse pump, I would say, they are characteristic of the presence of shots, blue shifted and red shifted. And of course, the most important thing for us is that here you can see on the V-Stokes, that's nice S-shaped, that nice splitting. So those patterns that we see in the stocks I, most importantly, they are similar shock patterns that we see in other pulsating stars like Kisik, which is an AGB stars, and RSQT that we just saw. So we are working on the best and the most accurate determination of the magnetic field intensity, although I can tell you that it's around 10 Gauss. So this is the same that what we already found earlier. So there's no big change in the intensity of the field. And something also that we have to take into account is that we had a change of instrument in between the monitoring from Narval to NeoNarval. So that's why we are recalibrating everything. Okay, something also that that is worth mentioning, it's on the same dates, in February 21 from the 13th to the 26th. So this is the 13th, this is the 14th, this is the 24th, the 25th, and you can see that line emerging. So I remind you that Luminocerotis is a cold star, let's say, effective temperature of 5000 K, but we can see that helium-1 5875 angstrom in emission. So that's a proof of shots. So what we and we had that that maximum emission of the helium line at that period of the light curve. So what we deduce is that the shock waves emerge from the photosphere around deep and shallow light minima. So the shocks emerge from here, and here this is where you have the I would say the collapse of the lines, and this is when you have the maximum intensity. This is where you can really well detect your magnetic fields. Something important is that, of course, those shock waves are not similar, for example, in intensity, so you would have, of course, different output in the magnetic field detection. So, in conclusion for that part, is the magnetic field subject to variation? Yes. Is the variability associated to any specific physical phenomenon? Well, it looks like that the magnetic field, the detection of the magnetic field is linked to the presence of shocks. The interferometric data, the follow-up didn't show any other indication that it would be linked to something else. And why it's important? It's important for the prediction, the observational strategy for the magnetic field detection. So now we won't go blindly to observe the objects, because the first time we did that, of course, we didn't have that back knowledge. So maybe we missed when the magnetic field was best, when it was the best time to detect the magnetic field. So we said that this or this star is not magnetic. This is not magnetic. In fact, it is. It's just that we missed when we should observe it. So now we have a good hint. Okay, let's jump to dust polarization. So we are changing wavelengths. We were in the optical. Now we are going to the submillimeter. So what we're going to do is to use the dust magnetic field relationship to involve the distribution of the magnetic fields. Here, I'm not talking about intensity. I'm just talking about the distribution, the geometry of the fields. So we conducted a series of observations, and those are the two newest targets, the planetary nebulae, the young planetary nebulae K335, and the water fountain W43A. So to do that, we use ALMA in band 7. So first, K335. So here you have an image of this object. This is a VLA image at 3.6. This is a continuum at 3.6 centimeter. So this is a young planetary nebulae with bipolar objects which are perpendicular to a ring of masers. It was detected by Uskorga et al. In 2008. Their circular polarization, there had been measurement of circular polarization in the OH with the OH masers by Miranda et al. In 2001 and by Wu and Gao in 2020. So in that case, there's not a clear relationship between the result that they obtain, well, the feature that they obtain with a Zeeman effect. But both authors suggested that if it is Zeeman effect, so the magnetic field will be between 0.9 and 4.5 milligauss. Okay, just a parenthesis. Before we were talking about 10 gauss, here we are talking about milligauss. We're not talking about kilogauss or megagauss. We are really far from that. We are really in the low regime of magnetic fields. So, as I said, we acquired data with ALMA, and the data were reduced with CASA, and we had a synthesized beam of 0.37 by 0.32 arc seconds. So this is the continuum. So you have this nice elongated structure here, like mostly like a type of S type, the same that I will show in that I showed you earlier, and that's consistent with previous studies. And now the polarization. So I want you to look at the beam, and I want you to look at the emission. So that was a big issue because the polarized emission is barely resolved. So we had to lower our threshold to 2.5 sigma to try to retrieve something. Generally, I do not go, thank you, I did not go below 3, but in that case, we wanted to see if there was something, so we lowered it at 2.5. And those are the polarization vector that you have that are aligned in that direction. The only issue is that that uniformity that we are seeing, but it's mostly due to the fact that the emission is very resolved. So we cannot really draw any possible correlation between the direction of those vectors. Those are magnetic vectors. We cannot draw any firm conclusion between the distribution of those vectors and the distribution of the magnetic fields in this object. So that might be the lack of, or the low polarization might be due to the dust grain size or the composition of this object. So this result is inconclusive. This is the same as we did, this is the same type of conclusion that we have with Frosty Leo. And I will jump into W43A. So this is a post-AGB, a water fountain object with narrow collimated jets. So here on the left, you can see the image, an ALMA image by Tafoya et al. In 2020. And just side by side, you have a model by Guillermo of the same object. So for that object, there was talk about magnetic launching. So Vleming et al. In 26 measured a magnetic field of 200, around 200 milligauss using H2O water lasers, and Garcia Segura as well used an MHD models to reproduce that shape. So this is the continuum of that source. So it's a boring elliptical continuum, nothing. But the polarization here, this is a 5 sigma cut. So yes, we do have signal. So we have what we can see. We have two lobes with two different polarizations. So it's basically twice the lobe on the south is twice, the polarization is twice that the one on the north. Those are the electric vectors. So here you can see that they are pretty well organized in each of those lobes. And you can also see that we have at some points, we have low polarizations. So I'm going to talk about that in a minute. So if we rotate our vector by 90 degrees, this is what we have. So we have the vectors going on that direction here. We studied the variation of the polarization angle, and we saw that there was like a S over here, and the magnetic vector are going in that direction in this the upper lobe. And again, we have those low polarization vectors here. So if we compare this with the object by the observation at 230 GHz, the continuum at 230 GHz that I just showed you, the image by Daniel Gabriel, we can see here again that is where our data encompass this continuum, and you can see again the variation, the different type of variation that we have in this object. So a bit bigger here. It's just to show you that when we did the polarization angle analysis, we can see that the magnetic field is really changing within the object. And those low polarization vectors that I was telling you about, they're generally due to the fact that we have, generally have the tangled magnetic field, that the vectors are in our line of sight. So all those change in the magnetic field distribution tell us that we have a tangled magnetic field, and generally tangled magnetic field are also linked to helical magnetic field. So I come back to the first talk that we had when we saw that model about those helical structures. And again, just to point out that those helical structures are also the one that we've seen in the Calabash Nebulae. So that would be the second example. So my conclusion here is that in terms of long-tail spectropolarimetric observation of the post-AGB star, now we will be able to predict when to measure the magnetic field. So we're going to be more efficient in terms of observation. The analysis of those two evolved stars, the one PN, one post-AGB. So one was inconclusive, the other one, W43A, shows some complex structure of the magnetic field that we associated to tangle or helical field. And that would be the base for a better model to understand the magnetic field distribution. And that's going to be the work of Guillermo. Thank you.
Thank you, Lourdes. Time for a couple of questions. So,
in the nice picture with a straight jet that you compared to Guillermo's magnetic shaping, I guess critical is, you measure a very small magnetic field in the nebula, right?
With that method, it's a bit difficult to measure the field. You talk about intensity. It's pretty difficult to do it.
Because of course the magnetic field at launch is very different.
Exactly.
Carried them by the gas out as it goes.
This is why we want to do combine our observation to some models. The models in the models we will put the exact intensity, and we will have some artificial polarization maps at that wavelength, and see
you
that
can
we
observe the model and then see,
exactly. So this is the next step.
Exactly, solved with the engine of the launching.
is unresolved. We need the event horizontal telescope, LBI.
But in the simulation, they're resolved.
Yeah, no, but observation
Yes,
will
of
need
course.
much better resolution. Even animals cannot resolve that.
Then you can see they're consistent, that's what.
Yes.
Say.
Yeah, that's the nice thing is that we are seeing those helical structures, but now we have to have more details on how this is launched, the characteristics and stuff like that.
Time for one more quick question.
Hi, very nice. It's more of a comment. There is a paper from 2021 from a postdoc that was at Chalmers, in which she fit a semi-analytical model to W43A, a jet semi-analytical model, and she gets a lot of constraints of what type of magnetic fields she needs. So I think it would be interesting for you to compare what you find to those predictions.
Thank you very much.
And I'm sorry, but the chair has to have a question here too. Lawrence, are you UMON and are they X-ray sources?
Human is.
UMON is an X.
Well, no, well,
Or Scooty is not.
okay, let me rephrase that. I don't know if Rudy is there. Yes, he's there. Okay, so Rudy find X-ray in that system, but not from the start.
Right, there's a companion or something.
Yeah, so maybe Rudy can tell you exactly, but this is not an X-ray source. The start humorousity is not an X-ray source. We found X-ray in the system.
And is there any periodicity in the shocks? Or do you not know yet? Too early to say?
The problem is that those even the light curves are not really periodic.
Yeah.
That's why I think they're not clocks.
Right.
So we didn't have to RSPT, they found like 2-3 months more or less.
It'd be so wonderful to be able to predict when you could look with X-rays and hope to find something.
Yeah, this is exactly what I told Rudy.
Let's thanks Laurent. Thank you, Laurence, again. And the last speaker of the morning before the coffee break is the poster pop-ups is Hans van Winkel. Hans's talk is about post-AGB stars and magnetic fields and jets from companions. Did I remember correctly?
Yes, okay, I'll.
Oh, yeah.
Okay.
Well,
anyway.
You want me to hold the microphone?
Okay, thanks for the organizers of this committee. So I will talk about a very specific type of objects, and a good, let's say, mental model of those type of objects is shown here. So you have a binary in the center. So you have a central binary. One of the components is a luminous post-CDB star or post-RGB star. The companion is a main sequence star, and they are surrounded by a massive rotating dusty disk. The limb of the disk is quite fat, so it's really a fat disk, and it extends from sublimation, which is typically a few AU, to a few hundred AU. The focus of today is really the companion and where the jet are launched. So this, or a whole list of collaborators in this work. The data I will talk about is, so we have a Mercator telescope and we built a spectrograph. And one of the motivations of me building the spectrograph is I'm interested in binary evolution. And all the objects of post-CDB star where we have a near-infrared access, that means you have dust near the system, these are those disk sources. So we started monitoring them, and there is a one-to-one correlation between finding the orbits, so binaries, to the presence of that near-infrared access. And so here are the orbits. So the orbits by themselves are quite telling. So it's a few hundred days to a few thousand days. When the star is pulsating, you need a lot of data because you have the pulsating amplitude and the orbital amplitude. And today I will talk mainly about those spectra. So these are just a few examples. The orbits are telling because these are systems that did not spiral in during the interaction, but during the interaction, they made the circumbinary disk, and that causes quite some interesting physics. So we know now that there is a central binary with a period of about a few hundred days to a few thousand days, and we don't see the companion, but we see the companion indirectly, and that's what the talk is about. Ivan gave already a talk about this the circumbinary disk, where we see a rotation in the center, we see some winds, and the interaction between the two is the focus of today's talk. Stay tuned, sorry. No, that's because we use interferometry to resolve the inner rim, and that is a paper about to be submitted. We used the interferometer to resolve 8 of those systems. Now, before I continue, I will present the data in a certain way. So in the x-axis, you have velocity. In the y-axis, you have orbital phase. And we show the data twice because we have 2 cycles. So it's orbital phase, so 0 to 1 and 1 to 2, just to guide the eye. This is just a photospheric line. You see the Keplerian velocity. On the right-hand side, you see a star with, a line with low excitation, which is linked to mass, which is not moving. So it's linked to gas within the system. And when you do that for H alpha, there is a certain structure that you see. And at some phase in the orbit, you see the appearance of a strong absorption component at high velocity. And that phase is when the companion is in front of the main star. So you don't see the companion directly, but you do see the impact of the companion in the velocity curve when the light from the main star goes through the outflow created by the companion. So the impact is quite clear. The phase coverage of this impact is also clear. So it's during a significant fraction of the orbit, you see it. And the interpretation, so you see it everywhere, in the sense that we have now 40 objects. You have to accumulate, of course, a lot of data because the orbits are 1,000 days. And there is a variety of morphologies, let's say. So here you see it's a narrow, sometimes you see it all the time. But in many objects, you have a signature of the light going through the outflow created by the companion. So how do we see that? We see the central star. That is the one that is giving the light. When there is an outflow, so there is a biponal outflow on the companion. And when the line of sight goes through that companion, or through the outflow, you see an absorption component. We never see an emission component. It's always in us. So phase covering is whenever you see a Pacini profile, so you see a high velocity absorption component, the line of sight of the main star goes through that component. How can you model that? So we use a geometric model in the first place. So we do modeling in several steps. You use a biconical outflow with some geometry. So you have the opening angle and you have a velocity which is dependent on the angle. So it's time resolved spectroscopy, and you use radiative transfer because it is in H alpha. So you need to have light, continuum light from the central star is scattered outside the light outside the beam because of the emission of a photon of an H alpha photon. So the parameters are jet optical angle, jet tilt, angular velocity structure, so the angular dependency of the velocity and the density structure. We know the binary, so we have an idea. So you probe, in fact, the structure of the jet by the time series. So left is the data, right is the model. So it works quite well, provided that you have a wide opening. So this is an example, for instance. This is the view of the binary. You have the binary, you have the Roche slope, and this is the preferential view in the plane of the binary, and this is when the conjunction appears. It's often that we see high velocity in the cone axis and lower velocity at the edge where the density is higher. When the aspect angle is quite high, so 89 Hercules, for instance, the aspect angle, we know from the CO interferometry that there is a bipolar outflow. We look at it quite all on, so in any orbital phase, you probe part of the jet. This is another one. This is a beautiful one I found because you see really a horn shape. This is the data, this is the model. And this is what it looks like if you just use the geometric modeling. We have about 40 objects. We didn't model them all, so that's work in progress. But let's say the analysis shows that the origin is the companion, of course. So the jet is created at the companion side. There is a wide opening angle. It's inclination dependent on how you view this in the time series. It's high density, low velocity at the edge of the bipone. And there is quite a lot of mass in this. And that is a problem because the mass that we get, or the mass loss that we get, is quite high. The outflow velocity, so the deep projected outflow velocity, is always a main sequence and never a white dwarf. So I mean, the escape velocity is typically a main sequence, escape velocity. Then the next model, so we go to physical models, and for that we use Young-Stellar object models, in the sense that we use NHD models for Young-Stellar objects. Those models, they exist with the central star and of course the accretion disk from the Young-Stellar object, but then we have to translate it to a different viewing angle. We don't see the central star, but we see the light source. We use the postage B star as a light source, probing the density of the jet. So the different parameters are the magnetization of the thing, also the inner edge and the outer edge. And one of the characteristics is that if the magnetic field of that star, of the Young star, is high, the inner ring is, because it's magnetically truncated, the launching radius is far from the star. When the magnetic field is low, the launching radius is close to the star because the disk extends up to the central star. So we don't see the central star, but we see the light from the postage B star through the nebula, through the bipone, and that helps us to, let's say, model the parameters of this type of model. So it's an MHD model that we use from the group in Grenada. It gives us the natural explanation for the velocity gradient, because all those models do have a velocity gradient where it's high in the cone and low at the edge. The density is here higher than there. You have a natural explanation for the wide opening angle. So jets are indeed wide if the magnetization is small. And the opening angle is such that it does naturally give us a good phase coverage during orbital motion. So the positive thing is that it's a good model for our jets. It's a cold, because it's a cold MHD disk wind, and it provides us quite good observables that are very similar to our spectrum. There are a few challenges. And so here you see, this is the data, this is the background spectrum, which we use as a background that goes through the jet, and this is after it has passed through that physical jet. And so you see the similarities. There are a few caveats, or there are a few problems. One, first of all, we need a very high mass loss. This is the accretion mass onto the companion, which is quite high. That means they're transient phenomena, or we are wrong with the mass estimates. But 10 to the minus 4, because it's 10 to the minus 5, you don't see it anymore in our spectrum. So it's a bit uncomfortably high, and we have to and the main reason is that it's always in absorption. So that means the gas is quite cold, because the background star can be 4,000 Kelvin, can be 8,000 Kelvin, but it's always in absorption. That means that the material of the jet is quite cold, meaning that there's not a lot of excitation to the first level because it's in H alpha. And so that gives us a quite high mass estimate, a bit uncomfortably high. Then another thing is, normally disks are rotating, so accretion disks, they rotate. That means that if you have a rotating disk and you have a rotating jet, part of the jet will come towards you and part will go away from you. That means you expect to see that rotation also in the data. And that means you would see also an absorption component on the right side, so on the red side of the H alpha, but it's never observed. So we have to find a way to suppress rotation to such a level that we don't see that accretion in our data. So that is still work ongoing. The thickness of the accretion disk would help. So there's an accretion disk around the companion then. And we did not in our model take into account the irradiation of the Perseid B star onto that disk, which could also have an impact on the thermal structure of that disk. So that's work in progress. So to conclude, we have a nice way to create jets. We see, thanks to our time series, we can probe the structure of those jets. The jets are always white. They are around the companion. And we have to see those objects as really interacting systems. So the properties of those systems are really, they are made during HB probably, so that you have a creation of the disk, but the interaction is still ongoing. So we have to look at them as interacting systems. There are many questions that are still, give us some future work. So, of course, the creation of the disk is important, the evolution of the disk is important, the structure of the circumbinary disk is important. We see grain growth, we see a lot of interesting physics going on, very similar to disks around young star objects. So to combine the two is quite important. We have the jet creation, and now we have a natural explanation for why jets. We have a natural explanation for the jet. These are old stars, so the magnetic field is not very strong. And so you see the outflow in companion. We can use the time series to trace the structure of the disk, so that's good. The lifetime of the jets is still a bit problematic because the mass that we derive is too high, or the mass loss or the mass accretion rate, let's say, is too high. So there is still quite, you count the number of questions, so we still have some work to do. Thank you.
What? Carmen, sorry.
Thank you very much, Hans, for the whole review. The jets, you see them in absorption in H alpha.
Yes, H beta and H gamma.
So what is the electron temperature you estimate for the jets?
We don't estimate the electron temperature because what we estimate the temperature, the highest temperature that is still giving an absorption component because of the background radiation. So if the background is 4,000 Kelvin, we have to have a jet which is lower in temperature, otherwise we'd see emission. And in all the systems, whether the background source is a 4,000 Kelvin or an 8,000 Kelvin, it's always an absorption. So it's quite cold.
It's not ionized.
No.
They're barely excited. Right?
Yeah.
It's barely excited.
It's barely excited. And that makes, because it's always an absorption, you have to have a low temperature when the background source is 4,000 Kelvin. And that makes that there are not many hydrogen in an excited state to create H alpha in the first place. And that makes it the tricky part where we get the high mass accretion, about the mass of the jet.
Yeah, and I was also surprised about the high accretion rate because this means that the accretion is very efficient, or
Yes.
the mass loss rate from the post-AGB is just crazy.
No, but we think that it's coming from the circumbinary disk. So it's not by accident that there is a stream from the circumbinary disk to the companion, because we also see that stream, or we see the effect of that stream onto the main star.
That makes sense.
That depletion there.
Thank you.
We'll go around this way, no, and then to the back.
But it's common, so we observe it in 40 objects till now, so we have enough data for it.
Hans,
Yes.
very beautiful. Why do you need to reduce the jet rotation? With the jet rotation because of the disk rotation?
Yes.
You don't see it in lines,
Yes,
but this is not from observation. This is from the model you use.
yes,
Let
So
me
it-
take- I don't know this theory. I know observations.
yes,
I know observation of young stellar object,
yes,
and in 3 or 4 or 5, I don't remember times, that people use model of magnetic
yeah,
press hoop and whatever, and they claim they see jet rotation. I always show them that this is not a jet rotation. So the models, which I'm not familiar with, I'm an observer, overestimate the rotation that we observers see in observation when we analyze it carefully. We my view is that we need to use observation to constrain theory, not to use theory to rule out observations.
No, but
So-
the accretion disk should rotate, eh?
The accretion should rotate.
And
But
so the
what
jet
we use-
launching,
No,
it's normal that you have an we have a rotation in impact.
Look, you don't know what's going on. What?
I observe.
Okay, I'm sorry, the chair has to step in now.
What's the
Questions in the back.
observation to detect the magnetic field and make it, large radius, taking. Large radius. Come on, I mean, I'm not saying, I tell you what, my observation.
No, but so, I mean,
Look at my paper of young Stella.
Next question.
Yeah, nice talk. It's the first time I hear about this. For how long would you expect the phenomenon to last? So I'm thinking of the variable H alpha emissions that we see in hot white dwarf plus like LOTR4 systems, which is also seems like too broad to just be chromospheric emission. And could that also be related to that?
well, it's difficult to answer in the sense that for the moment, it's a transient phenomenon. In the sense that if we are right with the high mass accretion rate, it will not last forever. It will not last long because the mass in the circumbinary disk will limit how much accretion you have onto the system. And if this is a few hundred of a solar mass, you can compute 10⁻⁴, 10,000 years. Much longer, much less long than it will not be a white dwarf in that time. So we first have to pin down the mass accretion rate and be more confident in our estimates before we can say something about the lifetime.
And I'm sorry, but we have to move on, or none of us will have coffee, and that would be a bad thing.
Yeah.
And we're gonna have 3 posters. I believe it's number 1, 2, and 48. Or it's one of them. Thank you. Let's see, who is first? Interesting combinations of chairs and former students. The first poster is by Rudy Montes, and he'll tell you what it's about.
This is to answer your question, Joel. You read this paper and you'll learn
Thank
about
you.
all of the X-ray emission from Mu monocerotis. This is an artist illustration of the system. It's got a circumbinary disk. It's we heard a lot about it from Laurence, and we heard a little bit from about it from Hans as well. I'm going to talk about. Well, I'm just highlighting that this is the paper that answers all your questions. The answer is that at Astron is when we would detect the X-rays. We think we would most likely detect the X-ray because that's when the companion is closer to the circumbinary disk, and that's when it'll accrete more material and produce this 10 megakelvin plasma that we detected from that system. This is by a former PhD student, Laura Vega, who's now at NASA Goddard, and she analyzed this huge light curve all the way back to 1890 as part of the analysis of that work. It's a multi-wavelength beast, this paper, so you should look at it. But that got us interested in looking for more X-ray sources from these types of systems. And that's what Nick Graber and I did in the summer of the pandemic. Nick Graber was in a summer REU program, undergraduate program, and had to do it remotely because of the pandemic. And so we just worked together on looking for all of these X-ray sources from other RV-Tau variable stars. And we found one, and we were so excited. Then we put it on the HR diagram, and it was not at all where it should be. It turned out it was a main sequence star, and that sent us down a long path of figuring out which of these RV-Tau stars that were in the SIMBAG catalog are actually RV-Tau stars. And so we looked at all of the light curves from the Assassin catalog, and we found some eclipsing binaries that were miscategorized as RV-Tau variable stars. We cleaned up that, produced a whole new list of bona fide RV-Tau stars and some that were not, identified those that were not. And then we did go look for more X-ray observations. This is from the RV-Tau variable star AC HER time. And we did not detect any X-rays from it, long story short. It looks like it's really rare to detect X-rays. Thank you.
Can you hear me? I am Alina from Çukurova University. I'm working with Professor Nazım Akseker, and thanks to Professor Parker, I'm here. Today I will briefly share our study on machine learning and PNE. We trained a CatBoost model. Thank you. We trained a machine learning model which is CatBoost with approximately 2000 spectral data from Hash database and the other archival sources. We labeled them, then we focused on 149 galactic planetary nebula candidates. So our models gives us say that these two could be planetary nebula, so we investigate them if they're really planetary nebula or not. As you can see, sorry. How can I make it bigger? Oh, okay. Can you make it bigger? Sorry. So we use diagnostical diagrams to make sure. Okay. Here you can see this is not a PN, and this is not a PN, close to PN, but not. But here, this is a PN. But we investigated those two too, because they have hydrogen gamma line here. So these were symbiotic stars. In summary, I'm a little bit excited, I'm sorry. We combine machine learning with classical diagnostics. So it improves the reliability of PN identification. Thanks for listening. Gracias. Enjoy your coffee.
Hi everyone, I'm Faiza Vijayjan and I want to talk about the development project. In this project, we used a Hubble telescope that is located in Terway to take the images. The main purpose of this project is to study the latest stage of the feedback of the effort star to the LSM. But before to achieve this purpose, we need to prepare the images. We spent a lot of time and money to take the images. As in our case, we 1,000 hours in 5 years. So it is important to choose the best tools for the prepare the data. And this is why we use GenoAstro. I can't find it.
The top bottom.
Yes. GenoAstro, that is a best powerful tool for analyzing and manipulating the data. You can see the OR pipeline in the first step. This is one exposure. And in the first step, we use GenoAstro noise cell to calculate and subtract the background, and you can see the out of the noise cell. In the next step, we align the images to the RACS coordinate. As you can see, there is you can see the effect of the Moore pattern. So we need to remove the Moore pattern in the next step, and we apply all the steps to all of the exposures, and And then we provide all images, and you can see the clean output here, and that the bad pixel are removed in the output of the provided output. Okay, please look at this box, and you can see some of the output of our pipeline, and you can see the large field of view and more details in this region, maybe in this region, and this. And this is why we use the master instead of AI. And if you have any question, please join us at coffee break. Thank you.
Very interesting session. Noam, I encourage you to talk to Hans and vice versa at the